The last item on our to-do list is to show that every regular set, that is, every set of strings accepted by some DFA, is generated by some regular expression. What the definition of regular set actually gives us for any regular set is a DFA accepting that set. So what this video is really about is how to take any given DFA and construct a regular expression for the language that DFA accepts. Our process works just as well for NFAs, so why not include them while we're at it? Let sigma be a finite alphabet and let m be an NFA over sigma. First of all, we'll need to prep our incoming DFA, or NFA, into the form we discussed previously, giving an NFA accepting the same language with 4 key properties. A unique accept state, distinct from the start state, with no transitions coming into the start state, and no transitions coming from the accept state. All 4 of these properties will be essential prerequisites for what follows. The second thing we'll need to do is extend our notion of NFA by allowing each transition to be labeled with a regular expression over sigma, for example, as in the NFA illustrated here. How does such an NFA operate? Well, as usual, we'll take any string x in sigma star as input, and we'll start with a single branch occupying the start state. The key difference is that, starting from our current position in the input string, rather than consuming a single symbol at a time, or none in the case of an epsilon transition, we move across one of these transitions by consuming any sequence of symbols matching the regular expression labeling it. The fact that a regular expression can match multiple strings makes this process inherently non-deterministic. For example, if we had the input string AAABA, we couldn't follow the left transition as no initial substring matches ABB. We could, on the other hand, follow the top transition on the right by consuming 0, 1, 2, or all 3 A's. Taking no A's, the branch dies because we can't then match BA. Taking 1 or 2 A's also kills the branch because we still can't match the BA. Taking all 3 A's allows the branch to proceed by consuming the BA and arriving at the accept state. Thus, because there's at least one branch finishing at the accept state, this NFA accepts the string AAABA. In contrast, any string not containing a B will be rejected by this machine. Both transitions to the accept state require at least one B, so no string without a B can get us to the accept state. In general, for any input string, this NFA accepts the string if some branch finishes an accept state and rejects if not, as usual. We'll use such generalized NFAs to simplify our NFA one step at a time to get an NFA accepting the same set, but having just a start state, an accept state, and a single transition. For our example NFA, we can see that the only way to pass through the state on the right and get to the accept state would be via a string matching A star, followed by the string BA. Thus, we can add a transition running straight from top to bottom, labeled by A star BA. This allows all the same strings to give a walk from top to bottom, but bypassing the middle state. We can then remove the middle state and all the transitions incident to it without changing the strings accepted by the NFA. Now we have 2 parallel transitions, and a branch could take either one. We can replace them with a single transition labeled by A star BA plus ABB, which matches all of the same strings. At this point, we can simply read off the regular expression needed to get from the start state to the accept state, finding that our new NFA accepts the set given by the regular expression A star BA plus ABB. The NFA we started with was quite simple, which made this process relatively easy. We'll have to be much more careful in general, but this does illustrate our strategy. Because there are no transitions into the start state, and none out of the accept state, all that we need to do is bypass and remove each state in the middle, one state at a time, combining parallel transitions via sums as necessary. When we're finished, just as in our example, we'll have a single transition from the start state to the accept state, and its label will give us a regular expression for the language accepted by the NFA. A few notes are worthwhile before we present the full details. First, our reading of these generalized NFAs is consistent with how we read a plain vanilla NFA, in which each transition is labeled with a single symbol of sigma or an epsilon. Indeed, the epsilon transitions were already a bit different than the ones with symbols of sigma on them, so in a small way we were reading NFAs in this regular expression manner all along. The key principle is that in either case, An accepted input string gives some branch that takes a walk from the start state to an accept state. And conversely, reading the sequence of labels along any walk from the start state to an accept state gives us a string, or a regular expression for strings, accepted by the finite automaton. Second, anytime we see parallel transitions that share the same from and to states, we can combine them via a sum. Third, any transition that we don't have could equivalently be considered to be a transition labeled by the empty set. In particular, we can think of every state as having a loop at it labeled with the empty set. This regular expression is unmatchable by any string, including the empty string, and thus it's impossible for a branch to follow such a transition, which has the same effect as the transition not being there. The details of the process that we'll use to bypass and remove one middle state at a time from our NFA are as follows. For any middle state, that is, any state other than the start state or the accept state, take note of three things. The transitions incoming from other states, which will color red. The transitions outgoing to other states, which will color blue. And the loop, if any, at that state, which will color green, along with the middle state itself. A quick remark on this diagram is in order. All the transitions here are distinct, because the red transitions are all incoming to the middle state from distinct states, and the blue transitions are all outgoing from the middle state to distinct states. The green loop is the only loop. However, it's possible that some red states are the same as some blue states. This causes no problem at all, as we will only change the red and blue transitions and not the red and blue states. Now, before removing the middle state, we need to form new transitions that get us directly from each red state to each blue state, bypassing the green state in the middle. These bypass transitions will each be labeled with a regular expression giving all possible strings that get us from one to the other, visiting only the green state in between. The label for each of these new transitions is a very straightforward concatenation of three regular expressions. First, the regular expression from the incoming transition, which gets us to our middle state. Then the asterisk of the regular expression on the loop, giving any number of loops of that middle state, followed by the regular expression from the outgoing transition, which finishes the journey. This means that if we start with m incoming transitions and n outgoing transitions, we'll form m times n new transitions, each with a regular expression giving all strings that get us from one to the other while only visiting our middle state in between. As we're only interested in strings that get us from the start state to the accept state, we can now remove the green middle state and all transitions incident to it, and we've reduced the number of middle states by 1. We simply iterate this process until we're left with only the start state and the accept state, with a regular expression for all strings getting us from one to the other as the label on the single transition. This regular expression gives the language accepted by our final NFA. As long as we can justify that our bypass and remove procedure doesn't change the language accepted, this regular expression also gives us the language accepted by our original NFA. So let's do that, and then we'll work through an example from start to finish. Consider the bypass and removal of some middle state, color-coding all of its neighboring states and transitions as before. Call the language accepted before this modification L original, and that after the change by L bypass. We need to show that L original equals L bypass. As usual, we have two things to show. First, that X in L original implies X in L bypass. Suppose that X is in L original. Then by definition, X gives some branch walking from the start state to the accept state of our original finite automaton. Along this walk, each time we arrive at the green state, we must arrive via one of the red transitions. Tracking our walk within the colored transitions, we must depart via one of the blue transitions, and until we do that, all that we can do is go around the green loop some number of times. As no walk from start to accept can start or finish at the green state, this is the only possible ways a walk from the start state to the accept state can encounter that green state. Such a segment of our walk gives us a regular expression matched by the corresponding bypass, so we can replace that segment of the walk by a walk along the corresponding bypass transition. In this way, we can eliminate from our walk every encounter of the green state, yielding a walk from the start state to the accept state in the new finite automaton that matches our input string. Thus, X is in L bypass. Second, we need to show that X in L bypass implies X is in L original. Suppose that X is in L bypass. Then by definition, X gives some branch walking from the start state to the accept state in our new finite automaton. Reversing our process above, we take each walk along a bypass transition and change it to a walk in our original finite automaton, along the corresponding red transition, an appropriate number of times around the green loop, and finally along the corresponding blue transition. This gives us a walk from the start state to the accept state in our original finite automaton, matching the input string, and thus x is in L original. Now that we've established that our bypass and remove procedure doesn't change the language in NFA accepts, let's run through an example from start to finish. This will get a little messy, so steel yourself for what we're about to do. Consider this NFA. First, we'll prep our NFA, adding a new start state with an epsilon transition to the old one, and a new accept state with an epsilon transition from the old one. We can also combine the parallel transitions from the left state to the top state, yielding just one labeled A plus B. Now we iteratively eliminate one middle state at a time until there are none left. Picking on the state at the right first. It has two incoming transitions and one outgoing transition, so we'll have two new transitions to form. Note that there are no loops to our chosen state, so we consider there to be a loop labeled by the empty set. From the state at the left to the bottom state, we add a transition labeled B empty set star A, or BA. Recall that the asterisk of the empty set is the singleton containing the empty string, so this contributes nothing to the regular expression. We add a transition directly from the top state to the bottom state, labeled by A empty set star A, or A squared. We can now remove the state at the right and all transitions incident to it, as we've created bypasses for them via our new transitions. Continuing on to eliminate the state at the bottom, we have two incoming transitions and two outgoing transitions, as well as a loop at that state, so we'll get 2 times 2 or 4 bypass transitions. Working with them one at a time, we have A squared B star epsilon from the top state to the accept state. We have A squared B star A from the top state to the state at the left. We have BA B star A from the state at the left back to itself, giving a new loop. This is what happens when a red state matches a blue state. And we have BA B star epsilon, or BAB star, from the left state to the accept state. Now we can eliminate the bottom state. Just 2 states left. Eliminating the state at the top, we again have 2 incoming and 2 outgoing transitions, and no loops. This will give us 4 bypass transitions. Working through them one at a time, from the state at the left back to the state at the left, we have A plus B, empty set star, A squared B star A, which combines with the loop already at the left state to give A plus B, A squared B star A, plus BA B star A. From the state at the left to the accept state, we have A plus B, empty set star, A squared B star, which combines with the pre-existing transition there to give BAB star plus A plus B, A squared B star. From the start state to the state at the left, we have epsilon, empty set star, A squared B star A. Finally, from the start state to the accept state, we have epsilon, empty set star, A squared B star. Oh boy, just one state left, and it has just one incoming transition, one outgoing transition, and a loop, giving a transition from the start state to the accept state, labeled by A squared B star A, times A plus B, A squared B star A, plus BAB star A, all asterised, times BAB star plus A plus B, A squared B star, which gets added to the transition already there to give our final result, which I'm not even going to read. This regular expression generates all strings that take us from the start state to the accept state in our final NFA, and thus also the language accepted by our original NFA. Well, that was rather hellish, but it got the job done. It can generate quite a mess, but the procedure is fairly simple in principle. First, prep the NFA. Then, one middle state at a time, eliminate the state and all transitions incident to it, after forming bypass transitions alpha, beta star, gamma for each pair of incoming and outgoing transitions. Don't forget to combine parallel transitions by adding their labels. Once all middle states are gone, you'll have a single transition from start state to accept state, labeled by a regular expression for the language accepted by the original NFA. If the original NFA happens to accept the empty set, you'll end up with no transition from the start state to the accept state when you're finished. Remember that this is the same as a transition labeled with the empty set, which is indeed the language accepted by such an NFA. In this video, we've checked off the last thing on our initial to-do list, showing that the language accepted by any DFA, and thus any NFA, can be expressed via a regular expression. Having shown that the two notions of regular set are equivalent, theoretically checks off the rest of the boxes on our to-do list. Specifically, the set of strings matching both of two regular expressions, and the set of strings that don't match a regular expression, can both be expressed by a regular expression. Most importantly, our results tell us that we have three logically equivalent formulations of what it means for a set of strings x over sigma to be regular. X is the language accepted by some DFA over sigma, X is the language accepted by some NFA over sigma, and X is the set of strings matching some regular expression over sigma. Each of these gives a way to show that a set of strings is regular. However, none allows us to directly show that a set is not regular. This will be the job of the pumping lemma, which we'll see shortly. Before that, though, we have one more topic on the positive side of things: how to minimize the number of states in a DFA, which yields some interesting results.